Thanks for joining the Temporal Graph Reading Group, everyone. And for today's talk, we'll be listening to Vinay on physics-informed GNNs conserving linear and angular momentum for dynamical systems. And a quick speaker introduction. So Vinay Sharma is currently a PhD researcher at EPFL in the Lab of Intelligence Maintenance and Operation Systems. His research focused on GNNs for modeling physical systems. Prior to joining EPFL, he spent 8 years at Michelin Research, where he worked on computational modeling, including finite element analysis, computational fluid dynamics, and material modeling. And he holds a master's degree in aerospace engineering from IIT Bombay. And I will hand the mic to you.
Thank you for the introduction. And so I would just, so the topic of my presentation today is physics-informed GNN, for which conserves a linear and angular momentum for dynamical systems. So going further, I will skip this bio slide. So the motivation comes for this is that in our lab and in general, we deal with these multi-body dynamical systems, which in general are driven by local interactions. So be it the gear systems or the bearings or even the human walking, you have these different joints, for example, in human, which are interacting with each other. So because of these pairwise interactions, the global dynamics of the system evolves. So the idea is that can we observe these systems and then understand what is happening inside them, normally which will not be able to measure. For example, if we can observe a rotating bearing, and can we observe what can we infer what are the forces on the rollers, or for example a human walking, and can we just from a video try to predict what are the forces. So this was the basic overarching goal of my research and generally what I do. Going further, just for this case, I would like to take an example of this simple case. So this is a spring mass system on which we have two nodes or two masses fixed at the end, and it is falling under gravity. And I have trained this simple system by using a simple GNN. And we see that GNNs are good for modeling such systems because they model interactions on the edges, and the dynamics of the system or the components is on the nodes. So this system was trained on these discrete set of masses, and then we test on something which is uh, within the distribution of the training. But when we apply such systems or such models to an extrapolation regime which has not been seen during the training, we see that it quickly uh, it is not able to unroll the whole dynamics pretty well. So this is the research gap that I was following to solve that. How can we model such interactions in these dynamical systems which are driven by these forces? So just to start, usually this has been done pretty well so far, is incorporating symmetry as an inductive bias. So we have rotation equivariance and translation invariance of these forces and the vectors, these physical quantities, which should follow such symmetry. And this has been quite well covered in the literature so far. But there is a problem here, which I will start to a little bit go into detail now. So there are two types of paradigms which can be used for incorporating symmetry. So one is the scalarization vectorization schemes, and the other is the high degree steerable schemes. Talking about the scalarization vectorization scheme, you have the node and edge features, and then from those edge features, you derive some invariant embeddings on the edges mostly, and then you decode a scalar coefficient, which you then multiply with a basis vector to get a vector message. It's kind of like you are first, you have the vector features, you are scalarizing them to create some embeddings, and then you're decoding them as vectors. So the biggest advantage of this is that if decoded carefully, you can get vector messages which will follow this anti-symmetry, that the message from node I to j can be set as the equal and opposite to for the opposite edge, for the complementary edge. And this is saying that conservation of linear momentum is possible if these messages model the internal forces. But however, in many state-of-the-art methods, these vector messages they end up being central, that is along the edges. And what is the problem here is to be sure. I will show this with the example. So imagine these two balls. Just a question: is the video okay, or
Yeah.
is it's stopping for you as well?
The video looks fine on our end, actually. It's pretty nice.
Okay.
Yeah. And just a quick question. Do you prefer questions during the talk or at the end of the talk for clarification and stuff?
I'm okay with during the talk as well.
Okay, thanks.
Yep, no problem. So in these standard scalarization methods where you have a single basis, usually what is predicted is interaction which is along the edge connecting the centers of these two spheres. So the problem is that although these forces are antisymmetric, but they cannot produce any angular motion. For infinitesimal time steps, predicting these central forces is okay. You can get away with that provided you are doing infinitesimal time steps. But if you do large time steps, then you have to account for some rigid body motions. And there, these central forces, they cannot model for large time steps the dynamics correctly as you see. So the dashed lines is what is how the model, how the system should behave. Now we can bring in some non-centrality. So in this case, what I just add is a frictional force acting on the centers, but you can still see that it diverges. The reason is the minute you bring the non-centrality, you need to account for another conservation. So central forces equal and opposite, it's not enough now because now you have to conserve the angular momentum as well. So here, in this case, although you conserve linear momentum, you don't conserve angular momentum. And this is the case where you can, if you conserve linear and angular momentum simultaneously, you can see that the friction over here, the friction forces should cause these spheres to rotate. And in turn, the dynamics should happen in such a way that the friction decreases as uh, uh, as the spheres rotate. So in a way that the friction energy should go into rotation as well. So this was the whole idea. And just to give a primer that when we should conserve linear and angular momentum, what I meant is here is that whenever these any two bodies are interacting, and if they are interacting with non-central forces, there are basically two vectors that has to be predicted. One is which usually predict is the exchange of linear momentum, which is equal to the force. But also there is something else, which is the exchange of the total angular momentum. And from that, you can derive the torques or the vectors that can change the rotational degree of freedom of these bodies. Another point is to make over here is to that these conservation of angular momentum is held about a reference point, and this reference point can be any arbitrary reference point in the entire coordinate system. So as I say, the conservation of linear momentum says that the exchange of linear momentum, and if you do it per unit time, it becomes force. They should be equal and opposite. And conservation of angular momentum, it's a little bit more involved. You can imagine that there are two bodies initially, both of them are rotating around their axis and they are also translating. So you have a component in the angular momentum, which is the rotational component, and the other one is the component which is due to translation about a fixed reference from point. Let's say this reference point is R naught. So the story just before the interaction is that each body has a total angular momentum. Just after the interaction, there is an exchange happens, and the exchange happens in such a way that the change in angular momentum of body I should be equal to the change in angular momentum of the body J, equal and opposite. So this is the conservation of angular momentum. And if you know conserve Aij, this vector, we can directly calculate the vector which can change the rotational degrees of freedom, because we have already predicted the force which changes the translational degree of freedom. We need to predict a vector which can change its rotational degree of freedom, which can we can just calculate using Aij minus this orbital component. And as a over here, this is actually this the angle moment of inertia times the change in angular velocity times this orbital component, and this orbital component is consists of change in velocity for a mass, which can be written as force, because per unit time this is just a force. So in our architecture we just do the same thing. We model bodies as a system as graphs, and then the key part is how do we predict something which is non-central. So the idea for us is that we predict or we construct local edge reference frames. This reference frames are done using vectors which are translation invariant and rotation equivariant, so they have the symmetry. But we do a series of Gram-Schmidt like orthogonalization in such a way that in the end we have for an edge ij these reference frames, and for the opposite complementary edge we will have an exact antisymmetric reference frame. All the basis vectors will be reversed, and this will become clear in a bit that why it is necessary. But before once we have the reference frame, we can project all our vector features on those reference frames to get some scalars, and then we can encode them those scalars to get these invariant scalar invariant embeddings. The next part is vectorization, where we decode these scalar invariant embeddings as coefficients of these reference frames. And this is where the antisymmetry of the reference frames is important. So as you can see, I can just predict three coefficients and this for each edge. And for edge ij and for the opposite edge, since these scalar invariant embeddings would be invariant, it would be same, my coefficients will just be the same for the edge ij and the complementary edge ji, and we have anti-symmetric reference frames which we can just scale the basis of these reference frames from the coefficients we decode from these edges, and then what we have is Fij is equal to minus Fji, very simply said, conservation of linear momentum. And similarly we can just decode this vector, as I told you, the angular exchange vector, so angular momentum exchange vector, in the same manner by scaling the basis of our reference frame in such a manner that Aij is equal to minus Aji. And one more thing is that we calculate for each edge a reference point, and this reference point is calculated as a weighted sum of each node's coordinate. And then what we get is a reference point which is similar for edge ij and edge ji. And just following what we do in physics, we can just calculate the rotational, uh, the vector which changes the rotational degree of freedom, that is the torque, which is neither symmetric nor antisymmetric. And then we use these decoded internal vectors in message passing, which is pretty standard, I would say. We just use those vectors to change uh, the velocity and the angular velocity of each node. And then we do this again and again in the message passing architecture. One thing that we add is a RNN style edge memory. So the edge embedding, invariant edge embedding that we have at layer L is used uh, again in layer L plus 1 as a combination. So it is just summed with the earlier edge embedding. So it definitely, in this case, when you do large time steps, uh, we end up in doing extrapolations. So even though this is uh, not a very hard case, we can do a long rollout easily. Uh, Even we can just fix a middle node and then it transitions to a chaotic pendulum. But the method shines in the case of 6 degree of freedom. So I will take an example of the 6 degree of freedom damped collision dynamics. Before I go there, I have to say how do we model the boundaries, because in these systems, boundary modeling is a pretty serious thing. So in methods like graph neural simulator, how you would model the boundary is that you will have a dense set of nodes. For example, in if you want to model this box, you will have a dense set of nodes representing each plane of this cuboid, and then if you have a sphere inside, it will form edges based on the distance with the the nodes which is close to it. And if you go to some recent more state of the art, then it becomes topological considerations you have to take. So here, for example, this node forms the edges with the faces of the mesh. But in our case, what we do is that we consider these boundaries as reflective surfaces. So each sphere or body inside this box is reflected around orthogonal along the perpendicular uh, to each surface. So we will have these virtual reflected nodes, and this is an addition. Like we have like for example in this case we will, for each node we have 6 times more nodes, but it is not that computationally heavy because the the interactions uh, are only kept which satisfy a threshold distance. So all of these interactions, they will filter off. So just a case is where we simulate this discrete element method. We use a discrete element method to simulate such trajectories. For example, these are 60 spheres colliding with the inside uh, uh, inside this cuboid, and then the walls are rough, and there is a coefficient of restitution, so there is loss of energy. And then we try to first do just a simple test where we uh, initialize uh, these spheres with a velocity which is not seen in the training case. So we see that we can do a long rollout for several hundreds of steps, and we capture the dynamics pretty well. So this visually it looks okay, but let's do some experiment here. So we have the same system which was trained on the 4 cases before, and then we set up a simple experiment where it becomes a closed system. So these two spheres, they are not rotating initially, they collide at an angle, and what will happen due to because of the friction, they will start rotating. And this over here, you're seeing the root mean square error of the final linear velocity of sphere 1 and sphere 2. And then we compare our method to several state-of-the-art method, for example, graph neural simulator, equivariant GNN, graph mechanics network, and CloughtNet. And this is our method. Uh, and these are all the re-implementations, because some of these methods are not in their original form applicable to 6 degrees of freedom. What is more important here is that to check whether we are doing the conservation of total linear momentum and angular momentum in all the axes. So this is the x, y, z components of total linear momentum and angular momentum. And this purple line is our method. Uh, for all the runs, we are able to pretty well capture the conservation. And this is the total kinetic energy, so this is a damped collision. So you should lose some kinetic energy. So uh, the black line shows the ground truth, and this purple line is our method. Which is very interesting over here is that all these newer methods like EGNN, GMN, etc., they are not able to capture the change in the total kinetic energy, this loss, but GNS is able to do it pretty well. So in all our experiments, we saw that for 6 degree of freedom, so we pretty much show our comparison with respect to GNS from now on. Another case of this we did like this in discrete element methods. There are these benchmarks, so to see how well are you doing. So in this case, it's a simple benchmark. The sphere is not rotating; it collides at an angle. So you can imagine that a, at a smaller angle, there will be a frictional force, which will be a tangential friction force, which will lead to rotation of these spheres after they collide. So we do this experiment for different angles. So this is the impact angles going from 10 to 90. So this is basically vertical drop. And then we see the resultant angular velocity in XYZ coordinates, and the orange is our method, black is the ground truth. We see that in except for this very small angle 10 degree, we pretty well capture the evolving dynamics. So this is the regime low friction and low restitution sliding happening, and this sliding causes these balls to rotate. The other one is interesting, where we have a different regime, which is the high friction high restitution case. And what is interesting over here is that at some angles the friction is so high that the ball sticks, and this will lead to a spin reversal. And we capture this over here. So this black is the ground truth, and you can see this is not following this trend, is because the friction angle causes spin reversal. And apart from that, let me go to case 2, where I can discuss a little bit more of the use case. So we train on just simple trajectories in the cube, which are 1000 time step long of 60 spheres and with different initial velocities. And then we have a wildly different coefficient of friction and restitutions for the sphere ball and sphere sphere interactions. And we also have an external gravitational force now. So in this simple case, we can predict the dynamics well. The idea is that doing these discrete element method simulations for complex use cases is difficult. Can we learn on simple system and extrapolate to complex systems? So once the simulation or the model has been learned over here, we test the model that, okay, can we then just apply it to a mixing case where we have several thousands of spheres and they are inside a cylinder, and the cylinder is rotating. Initially, the trajectories were inside a cubical box, and the cubical walls were not rotating. It was a stationary box. And not only the cylinder is rotating, it is accelerating. So it will go to a certain speed, stop, and then come back. How do we model the cylinder again? Is I just come back to what I said before, is we reflect the sphere. So we don't have to do any remeshing or remodeling. We just, if we know these surfaces and we take these surfaces as mirrors, we just reflect our spheres or whatever these spheres around the boundaries. And this is the result of this simulation, which goes on for, we have done it for 20,000 time steps continuously. Here I show you a speed up version of this simulation. So this is one shot we never trained on this system. In more, in these use cases, in these mixing cases, we also tested the GNS, graph neural simulator, giving the same wall reflection boundary method that we have for our method. We applied to GNS, and we see that after just 2000 times the simulation completely blows up. Um, in these use cases, we are mostly interested in some heuristics. For example, what is the average slope? In this case, the XZ surface slope over time steps. So where I show till 16,000 so time step, we are able to match the ground truth prediction quite well. Then there is a simple case of charged n-body dynamics. We train on just these simple configurations of three free particles, two sticks, and one hinges. So these are free, and then these are the constrained n-bodies. And then we do just a rollout for several time steps on a configuration which was not seen. So this is one free particle, zero sticks, and three hinges. And then we compare our method to different methods. So this is GNN. And then GNN augmentation is that we give an augmentation of the initial the data set. So we can because GNN is not by default rotation equivariant, we can just rotate our initial our data to give these augmented rotated data set or snapshots, which will help it to learn a little bit better. But we see that our method is doing quite well over here. But where it shines most is the rollouts. So where other methods quickly accumulate errors, this method is able to keep uh, uh, the integration errors in rollout pretty low. And then we tested this for large training sets. So this in blue is you're seeing our method. So this is to test the data efficiency, and on the y-axis you have the prediction error on the same case. And we see that this in pretty early it reaches kind of a stable point and just remains stable even if we go to 100,000 samples. As you see, this data-driven GNN starts becoming coming close when we have these 100,000 times 100,000 uh, samples. Then the case of human walking motion. This one is we have this CME motion capture data of a human walking. We give one snapshot, or we give snapshots for training, which are separated by 30 frames, and then we do the rollout for several time steps, which are at a delta of 30 frames. So we see that our model predicts well for the one time steps, but also rollouts. I would say starts accumulating errors at 3, but this is the well-known problem of the GNNs because this time step is too large, and as you start accumulating errors, and since your GNN is local, there is the localization problem. This is local message passing. You don't have any sort of kind of I would say hierarchical or global message passing. It accumulates error over here. But for the first three time steps, you can see that the state of the art methods, they just blow up in case of when they start accumulating integration errors. And in order to again show the diverse systems this method can be applied for, we just applied it on this ADK equilibrium data set where we have a protein in a solvent and we have to predict, given the data of frames separated by 15 frames, how the dynamics roll out. So here we are comparing with a hierarchical method, which is EGHN, which has also global edges. For example, if the protein is folding on itself, this method takes into account the edges between the folded atoms, but we keep the local backbone only. And this is we are investigating how we can do it, because just keeping the local backbone, we are still very good. Not as good as the other method, as it is hierarchical with the global edges, but still in the integration errors, um, we keep it stable. Another note that I missed saying for the human walking is that the rotational degrees of freedoms are evolved in these cases in the model itself, because we cannot help it. We are predicting the linear and angular momentum changes, but we don't compare those torques to anything, because we don't have that in the ground truth data. And then is a very new case that we just tried. It worked quite well. So in doing the gas dynamics or fluid mechanics, uh, we have like in the normal fluid mechanics in Euler equations, we have the appoint schemes, and those appoint schemes predict flux vectors which are non-central, so they are not aligned with the edges. In this case, our model is we found can also predict those flux vectors. So we have the three-dimensional momentum flux, we have the 1D mass flux, and a 1D energy flux, and that's it. And if we can just put them and in our framework where we predict the 3D momentum flux, which is the same as force actually, uh, and we also predict we can do some changes to predict these 1D antisymmetric mass and energy fluxes. We apply this to this pretty well-known data set, the well, where is these Euler multi-quadrants. So the you start with different pressures at the four quadrants, and you release the simulation, and then it rollouts. What is quite interesting is that we compare our method when we test on with these methods which is already there in the well data set. Uh, we do quite well, but what is interesting is that we trained on only one gas, and we can just extrapolate to other gases because we know the gamma and the gas parameters. This was all trained on 10 gases, and we have quite good extrapolation capabilities as well, where we have certain. I don't have time to go into these, but these OOD cases are is the pressure or the momentum regimes which the model never saw before. So this is to show that this method is applicable to diverse systems, even to continuum mechanics. Now, future directions, as I said, we are still affected by the locality of the graph message passing. Last time step require information propagation to far enough nodes, or even in case of, for example, the hyperbolic equations, Euler equations, the information of the pressure is passing with the speed of sound, and you need a lot of message passing, a large number of message passing steps to be able to do those fluid mechanics simulations. And this is what we are investigating, is that how can we tackle this, how can we tackle these hyperbolic cases, and essentially also parabolic and elliptic cases where the speed is infinite, so your whole domain should know what is happening at the other domain. So answer is hierarchical, obviously. Sorry, so we are exploring a hierarchical extension of this proposed method. Another thing that is quite interesting here, and I didn't present here, but we have some good results in this direction, is that this model is already predicting latent forces. So we have the moments and forces available. So can we correlate to something that is already measured? For example, not in the CMU motion capture case, you don't have the moments, but in there are some data sets, for example, at biomechanics, etc., where you have the motion of a human walking on force plates. And using inverse dynamics, you have the force and moments at the joints. So can we correlate what we are predicting to what was measured? So it's a good step in that direction where from just from purely observations, you can predict at least correlating forces, not magnitude wise, but direction wise uh, uh, on those joints. And then we are applying this to solid and fluid mechanics in continuum dynamics. So that's it from my side. I'm open for questions.
Yeah, thanks for sharing the interesting work, and you can see there's quite a bit of positive reaction from the audience, and feel free to unmute yourself for any questions, and yeah, uh,
Yeah, I have a quick question. First of all, thank you for the great talk. I'm curious about the reasons behind using like predicting dynamics. So like, don't we have deterministic formulas for most of these simulations? I'm just curious, what do we gain from using GNNs to predict these dynamics? Is it because the systems are too complex? Is it like an efficiency reason?
Okay. The most important reason is in order to do those deterministic cases, you need to know something about the material, so constitutive modeling or something. Here we are talking about learning just from observations. We don't know the rigidity, we don't know the damping, etc. So this is, I would not say, so this is one of the major case, and then the case about uh, efficiency. Yes, it is one of the case, not the important one, but this is one of the case. For example, in fluid dynamics, and not necessarily for human mechanics, let's say, uh, because there the number of nodes and the system is too small to do it. Surely in case of protein dynamics, so there is an efficiency, but for me, most of the most important case is learning from observations purely.
See, gotcha. Thank you.
yeah, and thanks for the discussion, and feel free to send your messages, like in the message as well. Uh, but if there is no question for now, we can also wrap up the talk, and let's thank again to the speaker for the great presentation. Yeah, and
Thank you.
Thank you
thank
for
you for
thank
coming
you
for
very
the talk.
much.
Thanks.
Thank you.
Thank you.